Piani, speaking with us here at the Zhejiang University Earth Data webinar. So Dr. Piani has been living in Nancy for many, many years, got both her undergraduate and a master's degree here before she moved to Paris for her PhD. And she spent a significant amount of her researcher's career in Nancy too at CRPG, but also she spent a couple of years at University Hokkaido in Japan. So today she's talking about the work that she published last year, and she's going to share with us more results relevant to it. So with that, I will leave the rest up for you. And normally our seminar goes for 40 to 45 minutes and leave another 15 to 20 minutes for interaction with the audience. So with that, here's your time.
Thank you very much. And thank you very much for the invitation. And it's a great pleasure to present my work to you and your group. So I'm going to, to speak about this recent paper we've published in Science last year about the Earth's water seen from the point of view of a cosmochemist. I mean, seen by the study of the meteorites. So the main message of this paper is that Earth could have formed from material that were present in the inner solar system that contain enough hydrogen to explain most of the present hydrogen that is in the mantle, but also a part of the hydrogen that is in the ocean today. And to introduce the objectives of this work, just let me remind some very usual facts, things that we all know, is that the Earth is covered by a very big amount of water. More than 70% of the Earth's surface correspond to the oceans, and we have also lakes and rivers and so on. But the main reservoir for water is probably not at the surface, but more in the interior of the Earth, with between 1 to more than 10 oceans of water that will be contained in the Earth's mantle. And the total Earth water is estimated by different proxies, and according to the different estimation, it could be between something like 0.2 to 2.4 weight% of water that will be in the whole Earth. The basic idea for the origin of water on Earth is that first the Earth formed from dry material that was present in the inner solar system, and that is probably close to a special type of meteorites that is called the enstatite chondrites. And these enstatite chondrites have a very similar composition, isotopic composition to the Earth rocks for a lot of different elements. So they are considered as some of probably our best analogs for the Earth building blocks. And this dry material then need to have some addition of water to make the Earth as we know it today. And the main hypothesis for the origin of water is that the water was delivered by hydrated asteroids, probably something like what we know in meteorites, the carbonaceous chondrites that can contain up to 10 weight% of water. And we need just a few percent of this carbonaceous chondrite to explain all the water on Earth. And this is the main hypothesis to explain the origin of water on Earth. So dry material to form the main part of the Earth, and the addition of hydrated asteroids, or maybe a bit of cometary material to bring the water. But this assumption is mainly based on the fact that the constituent material of the Earth was dry or devoid of hydrogen. And this is because the terrestrial planets and a part of the asteroids that are in the main belt are thought to form in the inner part of the solar system, where the temperature were too high in the first million of years of the solar system history to have water under the form of ice. So the water was under the vapor form and could not be incorporated with dust when the planetesimal are created. So the inner solar system planetesimals form dry. And this is also supported by the fact that the enstatite chondrites that are thought to be formed in the most inner part of the solar system were do not have any petrographic evidence for water. That is to say, they do not contain any phyllosilicates like we can find in carbonaceous chondrites, for example. So no hydrated minerals and no alteration phases that show that there were some water on their parent body. So this material is dry with no water evidence, no evidence for water at any time of the parent body history. And this is a great support for the inner solar system material form dry. So I presented the main hypothesis, so the delivery of water by hydrated bodies coming from the outer solar system, but there are other possible contributions or scenari to explain the origin of water on Earth. One is the fact that a part of the hydrogen contained in the nebular gas could interact with the molten Earth when the Earth was at the stage of a magma ocean and be in-gassed, be dissolved into this magma ocean and be kept in the interior of the Earth as inside the minerals and the magmas that are on Earth, in the interior of the Earth. So this was proposed for as a source of water on Earth that could contribute at least to the Earth's budget, water budget. Sorry. Another assumption was that some of the water can be also adsorbed at the surface of the silicates, and the adsorbed water can be kept even at a rather high temperature. And so the silicates that are free floating in space and can enter the inner solar system can keep a part of this adsorbed water, and so they can they can also contribute to the water budget of the terrestrial planets and the Earth. And another source for potential hydrogen or water in the terrestrial planets is the idea that some of the hydrogen can be implanted. So proton can be implanted in silicates and react with the silicate structure to form hydroxyl. And this hydroxyl would then provide some of the water to the Earth. And this implantation was proposed to be either in the interstellar medium, in interstellar silicates that will be then incorporated into the protoplanetary disk, or can also happen inside the protoplanetary disk by solar wind implantation. So this all can be a source of hydrogen that could contribute to the Earth. But of course, we need to explain also not only the amount of water, but we need to explain the isotopic composition of the hydrogen we have on Earth. And this different source would provide, at least for in-gassing and implantation, would provide probably a too low D2H ratio for the Earth, because the nebular gas is very depleted in deuterium comparing to the Earth's water. So we always need to balance the budget by the isotopes of hydrogen and the D2H ratio. So anyway, this means that we can have some hydrogen-bearing materials that can be present in the inner solar system material. And that even if we do not have any possibility to have water ice, we can still have hydrogen in this inner solar system materials. And in this study, we were wondering about the enstatite chondrites that are formed in the inner solar system and that are this very dry material. Do the enstatite chondrite have or not some hydrogen, and what is the D2H ratio of this hydrogen in enstatite chondrites? And we are using the enstatite chondrites as a proxy for the Earth's building blocks. So in fact, there were some value for the hydrogen content and D2H ratio of enstatite chondrites in literature, but this value are very scarce and not very consistent with one another, with value amount of water reported that were from less than 0.1 weight percent to more than 4 weight percent. That is very improbable given the fact that there is no hydrated minerals in enstatite chondrites, and also variable D2H composition. And probably one of the main problem of this data is that they were potentially modified by the terrestrial contamination, and also the meteorites that were measured are only only 6 enstatite chondrites, all being rather heated on their parent body asteroids, all being metamorphosed and modified by their history on their parent body asteroids. So in this study, we have conducted new bulk and in situ hydrogen analysis on enstatite chondrites having different degrees of metamorphism, and trying to target some of the most pristine one to have an idea of the amount of water that was in the primordial material of this meteorites. So here are the enstatite chondrites we have focused on in the study, and in particular we have done bulk analysis of the hydrogen content and isotopic ratio in 11 enstatite chondrites with 2 EH3. So the metamorphic type in meteorites is going from 3 to 6, with the 3 being the least altered, least metamorphosed, least heated meteorites, with and 6 being the most heated one. And of course, the most primitive are not the, unfortunately, not the most abundant on Earth. And so we have measured in the study 2 of this most pristine enstatite chondrites. And we also have measured different types. So 2 EH4 that have been a bit more heated, 2 H5 and 5 EL6 that are the most heated one. For comparison, we also measured 1 oberite, which is a chondrite counterpart of the enstatite chondrite, so differentiating meteorite. And we also measured 3 carbonaceous chondrites that were measured before in literature. That was, we need them to check our measurement and to compare in the same series of measurement the result between enstatite chondrite and carbonaceous chondrites. So we analyzed the bulk hydrogen content and D2H ratio using elemental and isotopic analyzer, IRMS for elemental analysis, isotope ratio mass spectrometer. And the way we did the measurement is quite common. We used some pieces of about 70 to 100 milligrams that we reduce in powder in mortar. And then we took aliquots of this powder between 10 to 15 milligrams for the enstatite chondrites. And then we put this aliquots into a tin crucible and put this crucible into a reactor that heat the material, melted it, and reduced the gases. And then the gases H2, CO, and 2 were separated in a chromatographic column, and then sent into an isotope ratio mass spectrometer to have the D2H ratio and the water content. So this is a very usual way to do this kind of measurement. But what we have done before the measurement is that we have degassed our sample to limit the atmospheric water adsorption. And to do that, we put our sample in a canister that was heated to 120 degrees C during 2 days under vacuum. And the goal of doing that is to remove a large amount of the atmospheric water without removing the water that is contained in the sample that is indigenous in the meteorites. And then the tin crucible with the sample, the powder was transferred to an autosampler using glove box and a dry atmosphere to avoid any recontamination of the powder before the analysis. And doing that for different meteorites, we have really seen the difference with and without this hot degassing, and we have shown in this recent paper, Vacher and collaborators in GCA, that it has a great important influence on the water content and dead-weight ratio of meteorites. So doing that, we obtained the water content of our series of enstatite chondrites. So here the water is reported, the hydrogen content is reported in water equivalent to compare to the numbers I've given you for the water on Earth, for example. And this is reported in a log scale, where you can see the different enstatite chondrite going from the least metamorphosed, the most pristine one in blue, to the more heated one in red. You have the obrite here and the carbonaceous chondrites in black. And as you can see, there is much less water in enstatite chondrites than in carbonaceous chondrites, but still we have some water, some hydrogen in this enstatite chondrite, with the most pristine one being the most enriched with 2.5 weight% of water. And if we look at the dead-weight ratio, here reported as using the delta notation, that is relative to the Earth's ocean water. So the Earth's ocean water is 0 here. All our enstatite chondrites are depleted in a deuterium, contrary to the CI type carbonaceous chondrite, and here we have the CM type carbonaceous chondrite. So the value we obtain for carbonaceous chondrites are quite common and totally consistent with previous measurements. But for the enstatite chondrite, we have always a depleted value with a delta D of about -100 to -130 per mil. If we look at the evolution of this dead-weight ratio and the water content as a function of the metamorphism, so the heating degree on the asteroid, the enstatite chondrite parent body, we can see that the most pristine one have the highest hydrogen content and also the highest dead-weight ratio, while the more heated one are depleted in water and enriched and depleted in deuterium as well. So we see a clear trend that goes from here to here with the increasing of the metamorphism in the enstatite chondrites. And for us, it was important to see this chtrend because, first of all, it's quite consistent. We expect to have less water in the most heated chondrites. But also the fact that we see this metamorphism trend allow us to say that what we are measuring in this chondrites, the hydrogen we are measuring, is mostly the hydrogen that was in the meteorites and not the effect of terrestrial contamination. And the decrease of the dead-weight ratio may be due to the loss of de-enriched organic components. Then, so as I've just shown, we measured some significant hydrogen content in the enstatite chondrite, and especially in the most pristine one. And the question now is, what are the hydrogen-bearing phases in enstatite chondrite, because we have seen that there is no phyllosilicates or hydrated minerals, so the hydrogen must be in another component. And here I take the example of Sarah 97 and 96, which is the EH3, that is one of the most pristine EH3. And this is also one that we have enough material to do more detailed analysis at our laboratory. So these meteorites have the highest content of water, 0.45 weight%. So if this is not the phyllosilicates, one possibility is that the hydrogen come from the organic matter that is contained in this enstatite chondrites. And we know that there is organic matter in enstatite chondrite, but the amount that was reported, so this is a study I have done during my PhD, but there are a few other studies that report the IOM content or the organic matter content in enstatite chondrite, and they are all consistent to say that there is not so much, the amount of organic matter is not very high in enstatite chondrites, and this organic matter is also depleted in hydrogen comparing to the one in carbonaceous chondrites. And so if we take all the hydrogen in this organic matter, we can only explain 0.04 weight% of water in the bulk rock, and it corresponds to less than 10% of this bulk rock value. So the organic matter can contribute to the water budget in enstatite chondrite, but it's not the main bearing phase. So what are the other possibilities? In fact, it's not that easy to know like this. Enstatite chondrites are a form of different components, mineralogical assemblages that we find also in other types of chondrites. The main constituent is chondrules that are silicate sphere made of pyroxene, a bit of olivine, glassy mesostasis, and also a few sulfides and metal. They contain also a few refractory inclusion. There's the calcium aluminum rich inclusion, but it's very tiny, rare phases in enstatite chondrite. They contain metal sulfide nodules that are mainly made of trollite, liningerite, aldamite, that are all some special sulfides that are found mainly in enstatite chondrites, and kamacite, which is the metal. And there is a few percent of matrix fine-grained materials that is a mixture between sulfides, silicates, metal, and this matrix is the place where you can find the organic matter. So in this study, to find bearing phases of hydrogen, we have focused our attention on chondrules, and I will explain why. So here you can see an electron microscope image of a chondrule in the enstatite chondrite Sarah 97 and 96, and this chondrule is made of mainly enstatite, which is reported in green here in the false color map. Olivine in a red, a few sulfides that are different types of sulfides, trollite, liningerite, aldamite, and we have this light blue areas that correspond to the glassy mesostasis. So this is a glass that is present in most of the chondrules in enstatite chondrite. And in fact, we know that this mesostasis is enriched in volatile and moderately volatile elements such as the sulfur, sodium, potassium, and chlorine. And this is enriched, of course, comparing to the minerals, but also comparing to the mesostasis in other types of chondrites, like carbonaceous chondrites or ordinary chondrites. So this means that probably when the chondrules form, they were formed under high partial pressure volatiles that allow the sulfur, sodium, potassium chloride to be incorporated in the chondrules, and especially in the very reduced condition in which this enstatite chondrite chondrule formed. And one question that arises from this study and observation is that if there are some volatile and moderately volatile elements of enrichment in the mesostasis of the enstatite chondrites, what about the hydrogen content of this mesostasis? And is nitrogen also able to be incorporated in this mesostasis and to be found in this mesostasis? So to target the mesostasis content, hydrogen content, and to measure its D2H ratio, we have used the secondary ion mass spectrometer SIMS IMS 1280 HR at CRPG. This is a picture of the instrument. So this instrument allows us to do targeted measurement at micron scale. And in fact, here we have done 10 by 10 microns rastering that give us a basic idea of the size of the measurements. And at this scale, we are able to target a specific phase, such as the mesostasis in chondrule. And so we have measured the hydrogen, deuterium, carbon, and silicon. And we use the H/silicon ratio to calibrate the instrument and to estimate the water content of the mesostasis. And to calibrate the instrument, we use different kinds of standards, basaltic, andesitic, rhyolitic, and phonolytic glasses. And doing that, we obtain a detection limit of 30 ppm. And also we were able to measure the D2H ratio with a precision or reproducibility for the standards that were of 40 per mil. So this is the kind of result we obtain represented here. This is a optic microscope image of an enstatite chondrite chondrule. You can see the enstatite minerals here and here, and all around this dark gray area correspond to the mesostasis, the glass, in which we have targeted some areas, and the black dots here, or the black area, correspond to the SIM spot we have done in this mesostasis. And for the 3 measurements reported here for this chondrule, we obtained very high amount of water, around 1% of water that is present in this glass. And we also always measure also quite a low D2H ratio with a delta D value of about minus 150 to minus 180. And we did that in 4 different chondrules, and at least 4 or 5 areas in each chondrules, and we obtain always quite a high amount of water, between 0.3 and 1.2 weight% of water, and with depleted D2H ratios. And an interesting observation is that the more enriched, the area that are the most enriched in hydrogen are also the sulfur-rich areas in this mesostasis. So it seems to have some correlation between the volatile contents for different elements in this glass. And here, this is the results that are reported in graphs that are similar to the one I presented for the bulk measurements. So you have here the water content in the different enstatite chondrite chondrules, and that is compared to the bulk. To the measurement we have done also in situ by SIMS in the mesostasis of 2 CV-type carbonaceous chondrites for comparison. And we choose these 2 CV-type carbonaceous chondrites because they have similar metamorphic grades to the enstatite chondrite SARA 97 or 86. And so we expect a similar parent body effect for this two different kinds of meteorites. And here on the right, this is the D2H ratio reported as a delta D notation for the different chondrules in Sahara 97 and 96 and for the carbonaceous chondrites. So what we found is the most interesting part is on the left, is that the water content in this glass, mesostasis glass of the enstatite chondrites is very much enriched in hydrogen comparing to the carbonaceous chondrites that are always on the hundreds of ppm level, when the enstatite chondrite mesostasis are always more than 2000 ppm of water and up to more than 1%. So the mesostasis is clearly one of the hydrogen-bearing phases in the enstatite chondrites. So we have tried to do a kind of budget of the enstatite chondrite mesostasis, the contribution of the enstatite chondrite mesostasis. So taking the volume percent of the mesostasis and the amount of chondrules in the enstatite chondrites, we estimated that there is about 0.07 weight percent of water that is inside the mesostasis of chondrules, and this corresponds to only 13% of the whole rock water content. So we have two H-bearing phases, but only 20% of the whole rock measurement. It corresponds to only 20% of the whole rock water. So it means that there are probably some other hydrogen-bearing phases, and so far we were not able to identify these phases. One possibility is that the pyroxene themselves, the enstatite contain significant amount of hydrogen, and in fact it was recently shown in the ordinary chondrites that the hydrogen content could be quite high in the pyroxene with up to 1,300 weight ppm. And but even taking this high value, we can only obtain 20% more of the whole rock hydrogen. So we still need to identify the hydrogen-bearing phases of the whole rock, and it means also that we have to be cautious with the bulk value that can still contain a part of the contamination, even if we are able to see a metamorphic trend or apparent body processes in the hydrogen content and D2H ratios. So that's why in the following discussion, I will always compare what we found with the bulk value and what we found in the identified carrier, the organics and the mesostasis. So here, I would like to discuss the implication of this result for the Earth water budget. So there were a lot of models to explain the abundance of elements and isotopes in Earth, and many models invoked a mixture of the different components that primordial component that we know in the solar system, and in particular the models are trying to explain the Earth's composition by a mixture of the different primitive meteorites, the chondrites, mixture of enstatite chondrite, EC, ordinary chondrite, OC, and the carbonaceous chondrite, CCs. So here I took not all the models, of course, but I tried to focus on some quite extreme models to see how much the enstatite chondrite could contribute to the Earth water budget. And here you can see three models. One is the Earth would be formed from 100% of enstatite chondrite. The other one derived from the work of Warren and proposed that the Earth formed from 30% of carbonaceous chondrite and 70% of enstatite chondrite. And in the third model, there is also a contribution of ordinary chondrites. So taking these three models, we have estimated the amount of water that can be provided by enstatite chondrite and the other types of meteorites. So this is what is reported here. So here you can see the water contribution in ocean equivalent this time. So one correspond to one ocean content, so all the amount of water that is contained at the Earth's surface. Then you have the range for the Earth's mantle between 1 to 10 oceans. And in purple is reported the water that will be provided by enstatite chondrite if the Earth formed from 100% of enstatite chondrite. So taking the bulk value we have measured, we obtain something like between 3.4 to more than 20 times the ocean content. And if we take now only the water that we have been able to identify in the mesostasis and the organic matter, we can explain about 4.6 times the amount of water that is in the Earth's ocean, which is not insignificant, and this is something that should be considered in the model. As I remember you that usually the enstatite chondrites are considered to be dry, so the amount of water that is provided by this enstatite chondrite is often set to 0 in the model. So now, if we compare to other models, with only 70% of enstatite chondrite, you can provide only around 3 oceans, but it's still 3 times the amount of water that is in the Earth's ocean. But of course, if you consider then 30%, for example, of carbonaceous chondrite, taking the CI type carbonaceous chondrite, which are the most enriched in water, with 10% of water, you can provide about 200 times the Earth's water. So in comparing to this CI chondrites, the three oceans provided by the enstatite chondrites is quite low. But this 30% is a very high extreme value for the carbonaceous chondrite that do not fit a lot of isotopic constraint. So still the water of enstatite chondrite should be considered, and especially the carbonaceous chondrite also have a much less enriched counterpart, water enriched counterpart, like the CO types and CD types. And in that case, the amount of water that will be bring by this carbonaceous chondrite will be less than 10, when the enstatite chondrite contribution is remains important comparing to this this value. And here for the ordinary chondrites, we also can have 10 oceans brought by ordinary chondrites. And with this 5% of carbonaceous chondrites, the enstatite chondrite contribution will be higher than the carbonaceous chondrite contribution if we consider not the most enriched carbonaceous chondrite, but least enriched carbonaceous chondrite. So just this slide is just to say that with the different proportion that were proposed in the literature and taking these extreme values, this extreme proportion, we always have a significant contribution of the water provided by the enstatite chondrite, and this should not be forgotten by when we do the Earth water budget in the models. Then we should look at the isotopes, because even if we can provide water, if the isotope composition is far from the one of the Earth rocks, it will not be consistent, and it would have to be explained. So here I reported the delta D value, so the D to H ratio has the delta notation of different objects, and you can see the value for the Earth water, 0, and the value that were measured in the Earth mantle rocks. And here is the probable value of the primitive Earth mantle, so something like between minus 75 per mil to minus 130 per mil. And what we observed is that the bulk and the mesostasis value is very consistent with that we obtain for enstatite chondrite is very consistent with this Earth's primitive mantle composition. Which is not the case for a lot of different kinds of chondrites. The ordinary chondrites are enriched in deuterium comparing to this value, more fitting the Earth ocean value, while the carbonaceous chondrites are very variable from one type to another and also inside a given type, for example, for CM. And you see that the Earth's primitive mantle values are almost not represented except for the CM chondrites. So this is very interesting because the enstatite chondrite D2H ratio is very close to the Earth's primitive mantle, but as you can see for the D2H ratio, it's not the only one, and the CM chondrites can also explain the value we have in the mantle. So to go further, we have also looked at other isotopes, and we look at the composition of nitrogen that were measured in another previous studies in this enstatite chondrites. So here I reported the nitrogen isotopic composition using the delta 15 nitrogen notation. And the 0 here correspond to the Earth atmospheric value. And on the x-axis, this is the delta D we have reported before. And so the surface reservoir of the Earth is at 0. And here in green, you can see the value that were measured for nitrogen and hydrogen in the mantle. And with here a value that could be a value for the primitive mantle. And if we plot the different chondrites, or at least the most relevant chondrites in this plot, you can see here the enstatite chondrites that fit well the primitive mantle value for hydrogen and nitrogen isotopic composition for both. And you can see with the other color, the hydrated chondrites, the CI in light blue and the CM type carbonaceous chondrites in dark blue here, and the CV and CO types carbonaceous chondrites that are in orange and red. And as you can see, so the primitive mantle is well fitted by the enstatite chondrite composition. So the primitive mantle, hydrogen and nitrogen could be derived from a source that is like the enstatite chondrite, and the CM type carbonaceous chondrites that cover the D2H range of the primitive mantle here do not fit well the nitrogen value for the primitive mantle. They are enriched in 15 nitrogen comparing to the primitive mantle. So with this graph, we can remove the CM chondrites for the origin of nitrogen, and thus say that the enstatite chondrite will be the best candidate. But then, if we want to explain the value we have now at the Earth's surface, the ocean and the atmosphere for the nitrogen, the enstatite chondrite value is not the good one. And there is, in fact, two possibilities. Either you have this value like an enstatite chondrite-like reservoir that is the main water contribution of the Earth, but then you have to find processes that would fractionate the D2H and the 15 nitrogen over 14 nitrogen ratio to explain the value we have now at the Earth surface. This is one possibility, but so far this kind of processes are not well understood or not known. And another possibility is that there is a mixing with a tiny amount of carbonaceous chondrite, and in particular the one which will fit well is the CI type carbonaceous chondrite that I reported here, the mean value. So if we take about 50% of the water coming from these two reservoirs, we can explain the value of the Earth's surface for nitrogen and hydrogen. And because this CI chondrite, carbonaceous chondrite, do contain a lot of water comparing to the enstatite chondrite, you need only something like between 4 and 15% of CI-like materials to explain this surface value. So we need only a tiny contribution of this CI-like chondrites to have the value of the Earth's surface. And for nitrogen, especially, we know that cometary contribution is also possible. That would even reduce the contribution of this CI-like material. So here come my conclusion. From our measurement, we can see that there is a significant hydrogen content in the enstatite chondrite, with whole rock composition going from 0.1 in the most heated one to 0.5 weight % of water in the most pristine one. The value, delta D value, is always depleted in deuterium comparing to the Earth's ocean. But is very consistent with the value that is thought to be the one of the primitive mantle. We can say that because we see parent body processes, there is not a lot of contribution of the terrestrial contamination. That was our first, that was something that was necessary to show before discussing the results, but still we were not able to identify all the carrier phases of this hydrogen in the enstatite chondrites. But anyway, taking the most certain value of the phases we have been able to identify, we have at least 3 oceans of water that can be provided by enstatite chondrites, given all different kinds of models that were made for making the Earth from this, from the primitive meteorites. And taking the hydrogen and nitrogen composition, isotopic composition, we see that these values are very consistent with the Earth's primitive mantle. So the enstatite chondrite-like material could be the main provider of the hydrogen and nitrogen in the interior of the Earth, for the interior of the Earth. And to explain the surface reservoirs, we need another 5 to 15% of carbonaceous-like material, or we need to find processes that would fractionate the isotopes from the enstatite-like value to the value of the atmosphere and oceans. So as an implication of this work, it means that in the inner solar system, there were some materials that do contain hydrogen. Of course, not as much as what we have in the outer solar system, but still the amount of hydrogen that is contained in the inner solar system material can be significant for the origin of water in the terrestrial planets. And this has also the implication that it can also provide a source for water in planets orbiting around other stars. And then now the question is how to incorporate and keep this hydrogen in the inner solar system materials. And especially we need to identify the hydrogen carriers in this enstatite chondrites and look at the speciation of this hydrogen in the mesostasis, in the glass, and in other phases that we can identify. And we should look at the process that would allow hydrogen to be incorporated into these chondrules and this chondrule mesostasis that contain up to 1 weight % of water. And we also would like to look at the presence of other volatiles such as nitrogen, carbon, and so on in this particular phases. So this is work in progress for the specific points. And I will stop my talk here, and I would be happy to respond to questions if you have any. Thank you for your attention.
Okay, thank you very much, Laurette. And now it's time for questions and of our participants. So before you ask a question, please let us know your name and your institution. Okay, I'm going to read a question from the audience that that typed in the chat box. So it's a very nice talk. In the conclusion slide, did you mean that the water in the mantle and the surface are decoupled?
Yes, in a sense. So, like, our study do not provide any constraint on the timing of arrival of any of the contributor to the Earth's water budget, but the fact that we see a signature in the mantle, the primitive mantle, that is different from the isotopic signature. I'm trying to come back here. Here, for example, to the Earth's surface, means either that you have a process that a physicochemical process that changed the isotope composition from this value to this value, or that you have a decoupling, as you said, between these two reservoirs. And a possibility is that when the Earth formed, it is made mainly of enstatite chondrite-like materials. So the main part of the Earth is made of this material and is represented by the primitive mantle value. And then at the end, probably of when the Earth was mostly formed, maybe like something like a lead veneer or even earlier, but still at the end of this process, you can add some carbonaceous chondrite-like material that would change the value of the Earth's ocean and atmosphere, but not change so much the value of the primitive mantle. That would be a decoupling, as you said, between these two reservoirs.
Okay, next question, please. Okay, here is a following question from the same participant that you have mentioned that more hydrogen in the sulfur-rich chondrules. Could you explain the reasons?
But this is something we are looking at right now. So in the previous study, we have studied this the sulfur content in the mesostasis, and we have seen that there are always a high sulfur content in this glass, in the glass, but that the sulfur content can vary from I don't remember exactly the value, but of several thousand of ppm, the amount of sulfur in the glass. And we have some chondrules that do contain more sulfur in their glass than other one. And if we take these chondrules with the highest amount of sulfur, we also find that it's the chondrules with the highest amount of hydrogen. So recently we have done some Raman spectroscopy to look at the speciation of hydrogen in the mesostasis. And what we have seen, also it has to be confirmed because we have a lot of fluorescence, and it's not always easy to find a clear area where we can measure the speciation of hydrogen in this glass. But anyway, several times we have seen the signature of HS bonds that would indicate that at least for some part of the mesostasis, the hydrogen is linked, physically linked to the sulfur inside the structure of the glass. So this can be an explanation why we have this correlation between the hydrogen and sulfur content in the glass.
Okay, thank you. And the next question, please. Actually, I have a quick question. That for the hydrogen isotope analysis, I think it's a very challenging task. That I don't know the technical details, but in my previous discussion with other people, it looks like the atmosphere correction is very challenging. Let's say. So I don't know that. What's your evaluation for this? Because do we? So how do we correct that atmosphere correction of the hydrogen isotope analysis by seems?
How to say? So first of all, we use for the hydrogen composition with SIMS, we use only samples that were prepared without resin. So they were polished with ethanol and then dried at 80 degrees for a while, for 2 days, before to be gold coated and put in the instrument. Then, as you said, it's very difficult to be sure to have removed all the atmospheric contamination in the sample. But what we have done in the study is that we compare the hydrogen content we have measured to the hydrogen content measured in other types of chondrites, in the mesostasis of other types of chondrites. And this one were one is a 6-section and the other one is thin section, but they do contain a bit of resin to glue the thin section to the glass mounts. So with this, for these two carbonaceous chondrite, the conditions are less, the preparation is less good as the one we have for the enstatite chondrite, but still we measured way less water in this carbonaceous chondrite than we have in enstatite chondrite. And we carefully checked at each area we have measured to see if there is no cracks or no special phases that were measured after the measurement using SEM. So I'm rather convinced that what we measure is the water of the mesostasis and the hydrogen of the mesostasis and not terrestrial contamination.
Okay, next question, please. That is from Yang Yanan from Institute of Geochemistry at the Chinese Academy of Sciences in Guangzhou.
Okay, hello, Laurie. Very nice talk. So in your conclusion that EC contributes a lot to the water content, right? You have the 3 models. The third model is that even, as I can see, even EC contributes a lot. So the CI may be still the most the significant contributor, right?
Yes, so these models, what I've done here is to take the most extreme values that may not be representative of what is in reality, but anyway, as you said, the CI can still contribute a lot if you take these proportions. Then you have to see that, for example, in this model or this models, if you take CI, the CI contribution, it's a huge 15 oceans here and 200 oceans here. So it's even not very realistic comparing to the amount of water that is on Earth now. So you have to lose a lot of water, then it will implicate probably a huge fractionation. And this do not consider any isotope constraint. It's just the amount of water that will be delivered by the different category or class of meteorites. So what I just want to say here is that we have to consider the enstatite chondrite as a contributor, like the other one. It's not correct to forget them completely.
Yeah, of course.
But then looking at the isotopes, and especially if we look at the nitrogen and hydrogen isotopes, then it's even more striking that the enstatite chondrite can be a very important contributor because they are the ones that fit the best the value we have in the mantle.
Okay, thank you. Another question is, so I'm just curious, when do you think the EC are created to the Earth? Before the moon forming event or after that?
Well, there is not so much constraint on the accretion timing of the enstatite chondrites. As far as I know, there is only a few values that were either derived from the thermal evolution of the parent body, or there is a recent value that was measured on the chondrule in enstatite chondrites. And it's something like 1.5 million years after CI, the timing of formation of chondrules, and also the enstatite chondrite formation will be quite early comparing to the carbonaceous chondrites. But it's still not very strong constraints that do exist for this enstatite chondrite parent bodies. But well, there's something I have not maybe be clear about is that probably the Earth's building blocks are not the enstatite chondrites, but will be derived from a similar reservoir as the enstatite chondrites. Because we know from the some elemental ratios, such as magnesium over silicon or aluminum and so on, that the enstatite chondrite do not fit well the Earth's composition. For isotopes, it's a very good analog, but for other, for elemental ratios, it's not that good. So probably it's the Earth will derive from material that come from a similar reservoir as the enstatite chondrite, but will be probably fractionated for the elemental ratios, at least, compared to this enstatite chondrite. So probably the timing of accretion of enstatite chondrite parent body is not that important comparing to the Earth formation. I don't know if I was clear with this response.
Thank you a lot.
You're welcome.
Okay, we could have one more quick question from the audience. You will have. Okay, if not, then let's wrap it up today. And thank you very much, Laurette, for giving us this great talk. And
I think there's someone.
thanks. Yeah, sorry. Do you see one more?
Oh,
sorry.
No?
I think that's, yeah, then that he asked a question earlier on.
So yeah, it appears now on my screen. Oh, sorry.
Yeah, he already asked a question. Yeah, okay, great. So we have perfect time. Okay, thanks everybody for participating, and thanks to the speaker for sharing the research with us. Thanks. Have a good day.
Have a good day.